In this lesson, we will take a look at a rule called the chain rule, which is a very nice rule that will make life easier for us. And it's basically a rule about differentiation, and it's about differentiation of complicated functions, such as the one that you see on the screen right now. What you have is here the cube root of sine of x squared plus 1. It looks like a really convoluted and complicated function. But if you think about it, we know how to differentiate each of the components. We know how to differentiate the cube root function, right, by the power rule. We know how to differentiate the sine function. And we know how to differentiate x squared plus 1 function. But how do we put all the pieces together to differentiate this function? That is the question of chain rule. First, we will take a look at the derivation of the rule, the actual rule, and then we'll take a look at some examples. Okay, so what we have here is a situation like this. You have y that is a function of u, and u that is further a function of x, and you could add more links to this chain. You could have x as a function of t and so forth. So you have basically three variables involved, or one function within another, like we've written over here. Y is f of u, y is a function of u, and that u is a function of further of x. How do you then differentiate dy dx? How do you find the derivative of the original function with respect to the last variable, which is x? And it basically boils down to a multiplication problem. If you take a look at what's happening over here, dy dx, we can write it as dy du times du dx. Because think about it, if you cancel the du's, you would be left with dy dx, right? Dy over dx. And these properties exist with the dy dx quantities, because remember, those come from like delta y, delta x type of quantities, and they do have similar properties, like in this case, the multiplication property, that the du's cancel. And if I had another variable down here with a t, I could further go down and say times dx over dt. Then you would be finding derivative from y with respect to t. Now the dx's would cancel also, and you would have dy over dt. Now, but for the simpler scenario, we just have y, u, and x, and the derivative of y with respect to x will be found as, first, by finding the derivative of y with respect to u, and multiplying that with the derivative of u with respect to x. Now, when we work with examples, this becomes a little bit cumbersome. We like to rewrite this as in a different format. For example, to write dy du, but that is the same thing as saying f prime of u, because remember, y was a function of u, right? So dy du is the same thing as f prime of u. And du dx, remember, u is a function of x, so du dx can be written as g prime of x. And the only other thing we need to remember is what u is, and again, since u is g of x, just substitute that in here, and thus we have what is known as the chain rule. And I put that in plain words. Let's read it, what it says. It says that first we need to differentiate the outer function, in this case f, leaving the inside function unchanged. We're leaving g of x exactly as it is. And then we're multiplying everything with the derivative of the inside function. Because just a reminder, once again, the original function that we were trying to differentiate was y equals f of u, and since u equals g of x, the original function that we were trying to differentiate was y equals f of g of x. And we have a convoluted function, an inside and an outside. Y equals f of g of x. So what we're saying is, to differentiate that, this is what we need to do. Differentiate the outside function first, leaving the inside function the same. and multiply that with the derivative of the inside. Okay, I'm going to summarize the results as follows. When we're finding the derivative of composition of functions such as f of g of x, the answer is first find the derivative of the outer function, leaving inside function the same, and multiply this by the derivative of the inside function. So this is the rule that we'll be using in most of our examples. Let's take a look at example 1. We want to differentiate 2x plus 1 to the second power. Now, method 1 doesn't use the chain rule. We can actually do this example by rewriting it as follows. Let's just go ahead and distribute the binomial. That would be 4x squared plus 4x plus 1. And now let's differentiate it. We get 8x plus 4. No need for the chain rule with this method. But think about what you would do if the power was the 10th power. We don't want to distribute this 10 times, FOIL it 10 times. It would be just way too messy. In that case, the chain rule will be very time saving. Now, method 2 uses the chain rule. The outside function is a squaring function. So first we're going to differentiate that. So bring the 2 down, subtract 1 from the power, leaving the inside unchanged. To the first power, I don't even need to bother putting that 1 down, and multiply this by the derivative of the inside. And if I simplify this by FOILing or multiplying it out, I get 4 times 2x plus 1, which is the same thing as we got above, 8x plus 4. So you can see the chain rule works, and in examples with higher powers, you will really understand how convenient it is to use the chain rule. So for instance, let's take a look at question number 2. The derivative will be start by differentiating the outside function. Subtracting 1 from the power, leaving the inside the same. And now multiply everything by the derivative of the inside, which is 6. If you simplify these, 6 times 4 is 24. And then we can write the rest. If you like, you may want to pause the video for the next few examples, try them first yourself, and then come back and see how we did them. Okay, here we go. Again, we can consider the square root power as the 1/2 power. So we bring the power down. Again, rewriting the expression if you like, with the 1/2 power. So now differentiating it, bring the 1/2 down, subtract 1 from the power, and multiply everything with the derivative of the inside. The 2's cancel, and we can bring the negative exponent quantity into the denominator. So we just have an x left on the top and a square root of x squared plus 1 on the bottom. All right, as for number 4, again, we want to find the derivative. First, by differentiating the outside function, leaving the inside the same, and then multiply this by the derivative of the inside, which is just a 2, and I put it up front so we're not tempted to multiply that 2 with the remaining argument of the cosine function. As a matter of fact, I should only have cosine of 2x minus 3. So first we differentiate the outside function sine, which was cosine, leaving the inside unchanged, and then we multiplied with the derivative of the inside. All right, let's try the next one. Same idea. Differentiate the tangent function, and we get this, leaving the inside function unchanged. And then multiply this with the derivative of the inside, which is 6x. Again, it might be suggested to put the 6x up front, so that we are not tempted in any way to multiply that with this quantity up there with the secant. Okay, a few more examples using the chain rule. Once again, I'm going to write this one without the square root and replacing the square root by the power of 1/2. Again, try it yourself first and then come back and check my answer. So the outside function is the 1/2 power function. The inside function is the x times tangent x function. When it is time to differentiate everything, to differentiate the inside, we will need to use which rule? The product rule, right? To differentiate x times tangent x, we will need that. So let's begin with the chain rule. So 1/2 times x tangent x to the power of -1/2 times the derivative of the inside. By the product rule, we have first times the derivative of the second plus the second times the derivative of the first. And rewriting all of this, just remember that the negative exponent can come in the denominator as positive 1/2 power, which is nothing but the square root. And that is our answer. And example number 7, we need to remember derivative of secant is secant times tangent. But multiplying everything with the derivative of the inside, we have an extra 5. Okay, next I suggest you try this example. And once again, when it's time to differentiate the inside, you will need the quotient rule. And when you're done, please come back and check your answer. And here is the answer to that question. So please try it yourself, pause the video, and come back and check your answer.